let us understand what is splatting. So splatting is basically a technique, it's a rendering technique where volumetric primitives are projected onto the screen and accumulated as soft footprints. So in splatting, what happens is that volumetric primitives, like here it is the 3D Gaussians. So these volumetric primitives, they are projected and they are thrown at the screen and they're accumulated as soft footprints. So that is splatting. So splatting means volumetric primitives. So for us, it is 3D Gaussians. They are ellipsoids of different shape, size, and orientation with different opacity and different color. So millions of ellipsoids, they are projected onto a 2D screen. Projected means we transform the 3D into 2D and they're projected and accumulated alpha compositing we do on the screen. So that is splatting. So in splatting, instead of rendering triangles, each primitive contributes a smooth 2D footprint. So see in mesh, what we do is that in mesh we render triangles because geometry is there. But here what we are doing is that we are just throwing or we are just projecting the volumetric primitives onto the screen and each primitive will contribute a smooth 2D footprint and this 2D footprint will be very smooth. Smooth in that sense that every pixel or every small region will be covered. So here contributions they blend together. So blending will happen. If, if we look at the historical context of volume splatting, so see traditional volume rendering if we talk about, so what we used to do traditionally in the classical approach, we used to do the ray marching. In the ray marching, what we used to do is that wherever the ray of the camera is falling, all the points along that ray, we sample them and then we used to feed all the points one by one to the neural network. And that neural network used to give us the 3D representation of that point, like what should be the color and all that. So that is ray marching. Now it is expensive and slow. It is slow because see the point is that neural network it takes time to generate the response and for every point we have to send it to the neural network one by one. So traditional volume rendering was like very inefficient. Then we had volume splatting, and this splatting is very efficient because we already have pre-integrated blobs. Like we already have 3D Gaussians, and they just get accumulated on the screen space, and we get real-time performance as we just now saw. So in order to understand splatting with a real life analogy, we can look into the snowball analogy. The idea is that you imagine that you are throwing soft snowballs at a wall. Each snowball will hit the ball, leaves a fuzzy circular mark. Many snowballs together they form a complete picture, and that is what is splatting is. And if we map this analogy to the 3D Gaussian splatting, because something similar is happening when we talk about 3D Gaussian splatting. So here we have snowball which is acting like a 3D Gaussian. Here snowball is the 3D Gaussian, wall is the image plane, snow mark is the 2D Gaussian projection, and layering is the alpha blending. Because in 3D Gaussian splatting, we have 3D Gaussian, we are projecting it on the screen. So the screen, the wall is the image plane, and the mark is the 2D Gaussian projection, and layering is the alpha blending. That is what we do. Now, why splatting works well? So see, in splatting, there is no need for joining any geometries. So no mesh connectivity is needed. naturally smooth surfaces we will get. It's a continuous representation, and it works well with optimization. It works very well with optimization, because in for optimization we need smooth surfaces. It has to be continuous. And see one more very interesting thing, like it works well with optimization. See, the idea is that when we will be optimizing, what we will be doing is that for every 3D Gaussian, we will be tweaking the parameters. We will be tweaking its position, the covariance. We will be tweaking the opacity and the color. And we'll keep on tweaking until the real image, until the rendered image is very similar to that of the real image. And what will happen is that when we'll tweak the parameters of a 3D Gaussian, it will contribute, it will reflect in the rendered image. It will reflect in the rendered image. And hence, splatting technique, it works very well with the optimization. It makes sense also, like millions of uh, 3D Gaussians, if we tweak their parameters, if we keep on changing the look and feel, the size, shape, orientation, it will affect the image, the generated image. And we'll keep on doing it until the rendered image is very similar to that of the original image. So splatting, it works very well with optimization.